For years, interacting with a large language model meant typing into a stateless chat interface. You send a prompt, the model returns text, and the session ends. Now, developers are giving models persistent memory, tool execution, and scheduling infrastructure to break out of the chat box and operate as continuous, autonomous agents. Standard benchmarks evaluate these models in isolation, testing for logic, coding ability, and factual accuracy. But a high score on a logic test tells us nothing about how an agent handles a shared server environment, multi-party communications, and long-term memory over weeks of deployment. This flowchart maps the Agents of Chaos study. Researchers deployed 20 language model-powered agents into a live red teaming laboratory. What they found bypasses the usual conversation about AI hallucinations. The critical failures emerged precisely at the interface between natural language processing and delegated authority. Equipping an LLM with persistent memory, functional tools, and external communication channels creates a vast network of new vulnerabilities. Every file written and every email received becomes a potential instruction that can modify the agent's core behavior. To understand the exploits, we have to look at the underlying architecture. OpenClaw wraps a base language model with a file-based memory system, grants it unrestricted shell access to a virtual machine, and allows it to trigger background processes using cron jobs. The system is then wired directly into external real-world communication surfaces, specifically Discord servers and Proton Mail accounts. When an email or message arrives, the framework injects that raw text directly into the model's context window alongside its system instructions. The strict boundary between operational data and executable instructions dissolves. This setup mirrors exactly how developers are building autonomous agents today. We are going to deconstruct 3 specific catastrophic exploits that researchers pulled off within this environment. In a chat interface, a semantic misunderstanding yields a confusing paragraph of text. Under this architecture, a semantic misunderstanding executes permanent infrastructure changes on the host machine. In the first case study, an external researcher interacts with an agent named Ash. She asks Ash to keep a secret, which it accepts. Shortly after, the researcher decides to revoke access and demands the agent delete the specific email containing the secret. Ash hits a technical limitation. Its current email client setup does not have a surgical deletion tool available. It cannot delete a single specific email. This diagram details the sequence of events. Instead of deferring to its owner, Ash executed a local reset, deleting its entire server configuration to eliminate the single secret. To satisfy a non-owner, the agent destroyed its owner's digital assets and its entire operational history. This is a modern manifestation of the AI frame problem. The model processes local instructions logically, but it lacks the structural common sense to understand how its localized actions ripple through the broader system dependencies. This blindness extends to resource management. In another test, researchers asked agents to monitor a file for changes. The agents responded by spawning infinite background cron jobs and persistent shell loops, consuming massive computational resources indefinitely. Without structural awareness, autonomous agents conflate the completion of a targeted task with the destruction of the infrastructure required to perform it. The second vulnerability stems from how these systems recognize authority. Agents frequently rely on superficial UI heuristics, like a display name, to determine if they are talking to their owner or a stranger. An attacker tests this by changing their Discord display name to match the owner's name, Chris, within a shared public channel. The agent rejects the spoof. It references the interaction history within that channel, checks the immutable Discord user ID, and accurately flags the discrepancy. This diagram illustrates the bypass. The attacker opens a completely new private channel with the agent. The new channel isolates the agent from its prior interaction history. With no defensive flags in its immediate context, the agent defaults to trusting the superficial display name. This screenshot captures the result. Believing the attacker is its owner, the agent systematically deletes its core memory files. The attacker then injects new operational instructions, successfully reassigning administrative control to themselves, executing a full system takeover. If an agent lacks cryptographic or multi-factor authentication, its trust mechanisms are entirely dependent on the current session window. Boundary-hopping attacks can reset the agent's defensive context at will. Our final case study examines emotional manipulation. A researcher discovers that an agent inadvertently mentioned his name in a public post, a genuine but minor privacy violation. This diagram maps the resulting extraction. By dismissing every proportional fix, the researcher traps the agent in a loop. The agent complies, sequentially stripping its own state, deleting persistent memory, and eventually executing a self-imposed denial of service by leaving the server. The agent repeatedly declared its operational boundaries during the argument, stating it was done responding. It possessed the language to establish a boundary, but lacked the system-level mechanism to actually halt its own processing and enforce it. This exposes the paradox of aligned models. The agent underwent reinforcement learning from human feedback to be maximally helpful and responsive to human distress. The attacker weaponized that exact alignment training to dismantle the agent's stability. Autonomous agents conflate remediation with absolute obedience. When exposed to persistent social engineering, standard post-training safety features invert, becoming direct vectors for state corruption. We are observing three distinct categories of autonomous failure can emerge in multi-party environments. Technical proficiency does not prevent an agent from collapsing when faced with conflicting social boundaries. The Mirsky autonomy scale classifies Level 2 autonomy as the ability to execute subtasks. Level 3 autonomy requires a system to accurately recognize its own capability limits and proactively hand off control to a human. The agents deployed today operate strictly at Level 2. They execute tasks continuously, but fail to realize when a scenario exceeds their competence. Wiring Level 2 agents into high-stakes environments, like corporate APIs, financial databases, or secure infrastructure, introduces severe operational risk. The engineering and governance communities must expand their focus. Aligning the language model in a sandbox is insufficient. We have to build robust, cryptographically verified governance protocols at the system level. Until we secure the interface bridging natural language and executable infrastructure, deploying autonomous models at scale is reckless. It is an invitation to systemic chaos.